The term brilliant solution was used to describe the Starship architecture, a fully reusable system designed to lift 100 metric tons beyond Earth, capable of orbital self-refueling, and ambitious enough to precede China in returning humans to the Moon. On paper, the mathematical inevitability of a 120-meter two-stage stainless steel vehicle powered by 33 Raptor engines producing 16.7 million pounds of thrust at liftoff seemed unassailable. Every variable had been measured, every tolerance meticulously modeled. Yet in practice, this system, built to defy gravity and accelerate timelines, repeatedly encountered the oldest law in aerospace, that physics does not negotiate. The design, which promised efficiency, carried a chain of risks that became invisible only as the system scaled. The original lunar architecture was defined by a profound structural dependency. The upper stage could not leave low Earth orbit without a complex and fragile ritual of in-orbit refueling. This strategy required up to 20 tanker flights for a single mission, a logistical solution that introduced hundreds of critical operations. This distributed complexity created what NASA analysts termed multi-event risk accumulation, where the failure of one valve, one rendezvous, or one minor delay would ripple through the entire sequence, making failure a statistical certainty over time. The commitment to this ballet of synchronized orbital maneuvers was not optional. It became structural to the entire industrial strategy and the core assumption of NASA's Artemis III contracts. Inside the plumbing of the cryogenic transfer lines, the physical constraints of microgravity defined the true barrier. The subcooled methane and liquid oxygen propellants behaved unpredictably without gravity, resisting orderly transfer. Turbulence and pressure drops, combined with intense solar radiation, caused asymmetric boil-off, a phenomenon where temperature gradients exceeding 5 degrees Celsius risked freezing or cavitating valves. These thermodynamic complexities introduced losses with every variable, meaning that each loss of propellant ultimately demanded another tanker flight, pushing the theoretical efficiency beyond the grasp of practical stability. This inherent fragility forced a quiet but powerful inversion in engineering logic, resurrecting the discarded idea of direct ascent. For decades, the energy required for Earth escape, lunar landing, and return demanded a propellant-mass ratio that every engineering review had deemed impossible, concluding the vehicle would either collapse under its own fuel weight or fail to reach orbit. The breakthrough was not a single invention, but a slow, cumulative progress. Incremental gains in engine thrust, material efficiency, and manufacturing tolerance. By the third integrated flight test, data confirmed that accumulated marginal improvements began to intersect the direct ascent zone, proving that a single-stage lunar return was mathematically feasible. This systemic shift was an act of engineering realism that carried profound moral implications for the geopolitical landscape. China's Chang'e program, relying on a disciplined, sequential approach using the Long March 10 and Lunar Orbit Rendezvous, prioritized incremental assurance. In contrast, the new Starship profile converted complexity into concentrated precision. The trade was fundamental. China's model distributed risk but consumed time. The American model concentrated risk into a single flight, trading coordination failure for absolute performance dependency on physics. The nation that could execute the simpler trajectory first would own the most valuable commodity, schedule margin. The decision to choose direct ascent immediately introduced a new, unresolved future vector of risk, transforming the system's vulnerability from external logistics to internal physics. Re-entry velocity increased, raising thermal loads on the spacecraft's heat shield by nearly 12%. The ceramic tile system, originally designed for Mars return, now faced higher intensity, shorter duration stresses, rendering the integrity of each tile's adhesive bond a critical part of mission assurance. A single detached tile could expose the stainless steel structure beneath to plasma at 1,600 degrees Celsius, a variable that remains unverified across a full-duration lunar return profile. Even the recovery system on the ground revealed its own mechanical paradox of precision. The Mechazilla tower, designed to catch the 70-meter booster with steel arms, was intended to enable rapid reuse. During static tests, the tower's hydraulic dampers experienced lateral loads exceeding 120% of their design prediction. A simulated capture landed 4 centimeters off-center, transferring asymmetric force that buckled a brace. The structure could handle the raw vertical impact, but only with a slower, gentler capture velocity, immediately negating the entire rapid turnaround target and revealing the mechanical limits of the brilliant solution. This conflict between engineered systems and their operational environment is not unique. finding an echo in earlier disasters that exposed structural cognitive error. The 1996 destruction of the Ariane 5 vehicle Flight 501 was traced not to a hardware flaw, but to a human decision to reuse an old software module from the Ariane 4. That module's 16-bit fixed-point data conversion routine was not revalidated for the Ariane 5's significantly higher horizontal velocity, which reached 3,071 meters per second. The value overflowed its allocated bit space, the guidance computer halted operations, and the self-destruct mechanism was triggered, confirming that a single, tiny mathematical error in a line of unquestioned code caused the complete loss of the system. Returning to the Starship ascent dynamics, engineers observed a continuous issue with the system's ability to stabilize propellant flow. Inside the plumbing carrying liquid methane and oxygen, the combination of pressure drop and structural vibration produced turbulence that led to microcavitation. This involved gas bubbles collapsing at sonic speeds against the metal channels, creating localized mechanical stress that degraded injector surfaces. Engineers logged the phenomenon as erosion fatigue, a form of progressive mechanical degradation that undermined the vehicle's capacity for rapid reusability by requiring extensive, unplanned refurbishment. This long-running instability culminated in the core causal inversion of Flight 4. During the booster's flip maneuver for the boost-back burn, telemetry recorded an uneven engine restart, producing a 4% thrust imbalance. Post-analysis quantified the true error. A software subroutine written as a safeguard to prevent overcooling introduced a 30-millisecond delay between the ignition of engine Group A and Group B. This infinitesimal fraction of time introduced by human design that prioritized thermal control cascaded through the system, producing the imbalance that ultimately destroyed the booster. The revelation was quantified with mechanical precision. The 0.03-second delay generated a differential thrust equivalent to 15 tons of lateral force, shifting the vehicle's center of mass off axis by 0.2 meters. The flight computer's subsequent attempt to compensate by vectoring engines increased local chamber pressure, and the resulting feedback oscillated across the engine cluster. Critically, the resonance frequency matched exactly 380 Hz, the booster's natural structural frequency at that specific point in the ascent profile. The vibrations reinforced instead of canceling, reaching a state of destructive interference that tore the structure apart under stresses below its design limit. The system was not overpowered. Its own specifications had amplified its destruction, proving that aerospace failure is defined not by weakness, but by precise timing. The post-flight review initiated immediate and specific engineering corrections across the program. Engineers rebuilt the propellant flow model, modifying sequencing algorithms and fully decoupling thermal management from ignition timing. The next booster prototype was fitted with dynamic dampers designed to absorb the destructive resonance peaks, and the Mechazilla tower underwent reinforcement to compensate for lateral capture loads. These structural and digital safeguards slowed the system by only 0.2 seconds, but this modest time penalty restored the fundamental necessity of operational stability, allowing testing to resume under a modified hierarchy. The direct ascent profile, now decoupled from orbital refueling, demanded a new level of propulsion precision. The total delta-V requirement for the surface-to-surface return is roughly 10.8 kilometers per second, demanding propellant mass fractions exceeding 90% of the vehicle's total launch mass. This was achieved because advanced Raptor engines operate at chamber pressures above 300 bar, providing efficiency beyond 380 seconds of specific impulse. These incremental seconds of gain, multiplied across the entire propellant load, were the precise mathematical conversion that shifted the mission from impossibility to viability. Yet the elimination of one failure source exposed the system to a new and more acute form of fragility. The loss of multi-launch redundancy meant that the system's margin for error compressed from hours to minutes, from kilometers to meters per second. The near-miss tension was confirmed in test ST-27C, where the vehicle achieved translunar injection, but a transient anomaly caused two Raptors to ignite 0.4 seconds late. The recorded thrust vector deviation of 0.7 degrees caused the vehicle to drift 38 kilometers off trajectory. If the guidance software had not corrected the burn within that 8-second window, the return corridor would have missed Earth by thousands of kilometers, proving that control logic saved the mission by less than 1 degree of precision. A more subtle vulnerability emerged from a hidden structure software feedback loop. Engineers discovered that the new internal tank geometry, which achieved a 25% capacity increase, caused the structural ring connecting the tanks to experience a cyclical strain exceeding its model limit by 0.3% during cryogenic contraction. This small mechanical strain caused sensor noise in the pressure and flow telemetry at 12 Hz, which aligned with the engine thrust oscillation. The avionics software, programmed to smooth these fluctuations, assumed the noise was random, instead slightly overcorrecting pressure regulation valves. This algorithmic error introduced flow oscillations that, over hours, could deviate the total usable propellant margin by several hundred kilograms, demonstrating how structural fatigue and logical error can merge to erode mission viability from within. The systemic risk of the geopolitical timeline amplifies this new fragility. China's careful incremental Chang'e program, while designed for reliability, advances on a 2030 timeline. The U.S. Artemis schedule, dependent on Starship, required the human landing system variant to demonstrate readiness before 2027. Each booster failure and subsequent redesign consumed months, placing the U.S. in the unique position of reacting to a foreign nation's lunar calendar for the first time since Apollo. The Long March 10's multi-stage, sequential approach consumes time, but the Starship's single launch profile must achieve absolute, one-shot perfection. The race is no longer against a rival, but against the unforgiving schedule set by reality itself. The moral clarity derived from this engineering saga is absolute. For years, orbital refueling was defended because the mathematics supported it, but the error was an assumption that today's material and thrust limitations were permanent. The eventual direct ascent breakthrough confirmed that impossibility is often a placeholder for incomplete data. When human design admitted its limits and traded complex choreography for concentrated force, it revealed that the physics of failure is a consequence of discipline, not desire, offering neither cruelty nor mercy, only truth. Today, the most recent Starship stands on the pad with an upgraded future vector, integrating dynamic damping, synchronized engine logic, and insulated refueling lines. The lessons of timing have been algorithmically written into its code, yet the deepest controlled uncertainty endures. The system remains the most powerful ever constructed and the only one capable of meeting the Artemis objective in time, but it has not yet demonstrated orbital refueling, lunar descent, and rapid reuse in a single successful campaign. The system no longer risks collapse under its own mass or complexity, but under its own precision. The question is not whether the Starship can reach the moon, but whether its engineers can keep identifying the invisible boundary before the physical law closes the margin.